Now, as we talk about the energy equation, and specifically as we start applying this to piping systems, we have to understand what's going on with the fluid flow. Because depending on what the flow is, things are going to happen differently. And so flow is going to fall under basically two broad classifications. So let's say that I had a tube, and then I put a needle in it that I can inject dye, and then I have some low flow rate, some low Q rate. So what is going to happen with the dye? Well, what we'll see is the dye will just go down along with the tube. It'll be moving in a very, very orderly fashion. If I take the same tube, same dye, I start and I kick up the speed and I give it a high flow rate. What's going to end up happening with the fluid? Well, it's going to come, you're going to see it's going to start mixing up and being really chaotic. And so basically this is showing you what is happening with these two different flow regimes. And depending on where we're at, we're going to have different things. So that very first one is what we're going to call laminar flow. Laminar flow is smooth, ordered, uniform, and because of that we're able to really apply some nice equations to it because we can mathematically predict exactly what's going on. So what you see here is this is a tube, a test tube, and we're shooting out a fluid, and notice that right along these edges here, everything's nice and smooth and it's clean. You can see this if you go to one of the sinks that has the high neck on it and just turn it on really slowly. You'll see it'll come out nice and smooth. I was going to say that if you're around campus, people can't smoke anymore, but if you know anybody that smokes, if you look at the cigarette, you'll get a nice smooth, orderly smoke coming out of the cigarette right near the cigarette. That's an example of the gaseous phase. Now, when we kick things up and make things go a little bit faster, this is what we call a turbulent flow. Turbulent flows are a chaotic flow. It's full of transient eddies of variable size and directions. That's why the dye mixes up. It's very chaotic, and it's difficult to predict exactly what's going on in the way that we would laminar flow. In fact, you can see right here, this is the same flow out of the same test tube. The flow is all wobbly and it's not smooth any longer. Going back to the example of the sink, if you're looking at it, eventually you'll come down, it will transition from a laminar to turbulent, and you'll see your nice smooth line, your nice smooth cylinder of fluid will start to break up and start to wobble like this. Going back to the cigarette example, eventually, once the smoke raises enough from the cigarette, you'll see the same thing. It will transition into a turbulent flow and start to break apart. So if we look at a sketch of this, so here's our laminar and our turbulent flow. Once again, orderly. This is a big thing about laminar flow. You can see it. It's all in straight levels. It's all in just little chunks. It looks great. Turbulent flow, chaotic. I can't spell chaotic today. Chaotic flow. Things are going crazy. It's moving around. You see streamlines are crossing each other. We have a bunch of weird little eddies and twists in it. And that'll make things kind of interesting to calculate out. So, next let's look at this video. I've got this little video here. This is actually a video, you can see this is my dye that I was talking about. Here's a laminar flow situation, and here it goes to a turbulent. And so it all starts to, especially through here, it all starts to mix up. And that's what's happening inside of the flows. Now, I was very impressed a few years ago that there was an American company that thought so highly of this idea of Americans knowing the difference between laminar flow and turbulent flow that they put a commercial into the Super Bowl. And that's not cheap. So they really felt strongly about this. And so I went and dug up the commercial to show you guys, and I'm just very impressed with the company. So if you take a look at it, laminar flow, turbulent flow, laminar flow, And so I am very impressed with the Miller Corporation that they thought so much of this topic that they took out an ad in the Super Bowl to show it off. Now, I know that's kind of silly and everything, but that's probably one of the things that'll stick in your mind now when you think about it because it's there. So the question now becomes, though, okay, great. You've told me that I have a laminar and a turbulent flow, and that has something to do with the energy equation. We haven't gotten there yet, but how do I know if my flow is laminar or turbulent? Well, it's all going to come down to Reynolds number. Yes, Mr. Reynolds is here again. So Reynolds number, that entire idea of I have the inertia force and the viscous forces working together, that I can sit here and calculate out by Reynolds number what flow regime I'm going to be in. So if we look in general, so this is just in general everything, we can look at the different regimes. These are interesting, but these do not directly apply to piping systems. So I'll let you guys take a look at them. I'm not really going to talk much about them. But once we bound the flow inside a pipe and we start looking at things and we start making some assumptions, that's when we can say, okay, well, this Reynolds number equates to this kind of flow. So typically in pipes, if we're below a Reynolds number of 2300, we assume that's a laminar flow. Depending on the book that you look at, it could be as low as 2000, it could be as high as 2500, but in that general area is laminar flow. Anything above 4300, we call fully turbulent flow. Now, once again, depending on the book, it can be anywhere from 4000 to 4500. That area that we have between 2300 and 4300 is what we call transitional flow. Now, transitional flow is kind of odd because parts of the flow are turbulent, parts of the flow are laminar, and it's really hard to predict. Now, as you're going to see, we're actually going to be able to do some predictive stuff with turbulent flow because at least it's chaotic, but it follows a certain pattern. Transitional flow, we're not going to be able to do that. Typically, you want to stay away from transitional flow just because you can't predict what's going on, and so your numbers are generally going to end up being wrong. So typically we're looking at that laminar and fully turbulent flow regimes. And once again, the way that we calculate this out is by using Reynolds number. So if we remember, Reynolds number is that balance of inertia to viscous forces. And so for pipes, we're going to be using Reynolds number sub D. Now what the sub D represents, all that is to remind me, because remember my Reynolds number, we calculated out. What is Reynolds number? Well, that was rho VL over mu, or VL over nu. That characteristic length, the length over which the interesting stuff happens. One of the biggest problems that I see students make is when they calculate out Reynolds number for pipes, they're calculating it along the pipe length. That is not where the interesting stuff happens in a pipe. It's across the diameter. So we use Reynolds number sub D to remind us, oh yeah, my characteristic length is my diameter. So my Reynolds number would be rho VD over mu, density, velocity, diameter over absolute viscosity, or VD over mu. Remember, mu is our kinematic viscosity, which you can look up, or if you wanted to calculate it, kinematic viscosity is mu over rho. That is our most sciencey equation because it's all nothing but Greek letters. So this is how we're going to figure out what regime we're in.